So question 5, this is the photoelectric effect question. Electromagnetic radiation is incident upon this photoemissive surface here. And the electrons will then jump off and travel towards this wire electrode here. Explain why there is a current only if the frequency of the electromagnetic radiation is above a certain value. So this is explain the photoelectric effect in slightly different dressed up language. So the first thing you need to say when talking about the photoelectric effect is always that each photon interacts with just one electron. Okay, it's absolutely critical whenever you talk about the photoelectric effect that you understand that each photon only interacts with one electron. If the energy of the photon, so therefore the frequency, is large enough, if the energy of the photon is large enough above a certain so that's above a certain value called the work function, then photoelectrons are emitted. Right, so essentially if you fire in a photon like so, if it doesn't have enough energy to boot one of these electrons out, then it can never do it. If it does have more energy than the energy required to boot one out, then every so often when it does, it will succeed in booting an electron out, and that electron will then fly off with the remaining energy. So the energy that the photon had, take away the amount of energy that it took to boot it out. So state and explain the effect on the current. State and explain the effect on the current when the intensity of electromagnetic radiation is increased. So if you have a more intensity, that means more photons, so you get more electrons, and that would therefore increase the current. So more intensity means more photons, so more photoelectrons per second, so a greater current. Okay, so that's an important thing to remember. When you increase the intensity of the light, you increase the current. Right, so there's a bit of blurb here about stopping potentials, and then we're into a question, but actually this bit isn't dreadfully important. The question is quite straightforward. We need to use the photoelectric effect equation, which is located on the formula sheet. And it's down here, photoelectricity. So that's the equation that we're going to use. So the kinetic energy max is equal to the energy of the photon take away the work function. So you've got the photon coming in, it has so much energy. You need to lose the amount that it takes to boot it out, to boot the electron out, and then any left over, so the amount that you had in, take away that, the amount that you need to boot it out. The amount that's left over is the maximum kinetic energy that's left to throw the electron out. So we just need to put the numbers in here. So H is on the formula sheet, 6.63 times 10 to the minus 34, times by the frequency, which is there, 7.23 times 10 to the 14. We need to take away the work function, which is 2.1, and then we need to convert the work function into joules, because this currently is in joules here, so we need to work this one out in joules as well. So 1.6 times 10 to the minus 19. So to convert from EV into joules, you just times by the charge on the electron. So we can put that all into calculator. 6.63 times 10 to the minus 34 times by 7.23 times 10 to the 14. And then we take away all of this in brackets. So 2.1 times 1.6 times 10 to the minus 19, close bracket. And we get that amount, which seems about reasonable. It's times 10 to the minus 19 there. If you got a really big number there, it's probably because you forgot, or a minus number, you forgot to change that into joules. So that's 1.43349 times 10 to the minus 19. So the maximum kinetic energy, that's 3 significant figures, but that's only 2, so we have to write it to 2. So that's 1.4 times 10 to the minus 19 joules to SF. So use your answer to question 5.3 to calculate the stopping potential for the photoemissive surface. Right, so this question is actually a lot easier than it might sound. You might get a bit confused by this, but essentially what you can do here is, as the electrons are moving off here like that towards that, if you make this side here more negative and this side more positive, you're going to pull them back like so. And if you make this side negative here and this side positive here, so you pull them back. Now, if they have the maximum kinetic energy, which means they'll just get to there before they come back, then that's the potential difference there that stops any from getting through. So what you do is you just adjust the potential difference until you're just stopping them from getting to there. So they almost reach, but then they're pulled back. And that's called the stopping potential. And it's just the energy of the photon in electron volts. So all we need to do is to convert this into electron volts, and then that will tell us how many volts it is. So the energy in EV is our answer divided by 1.6 times 10 to the minus 19. So hopefully that's still on our calculator, yes. Divided by 1.6 times 10 to the minus 19 gives us 0.8959 eV. So that is the energy per electron, but that's what we're trying to stop, 1 electron. So this amount here is the energy that is the maximum amount of kinetic energy that each electron has. We're only talking about 1 electron, so that is the potential that you have to put across here to stop it. So it's the same as that. So let's round it. So that's to 2SF, like so. If the student increases the frequency of the electromagnetic radiation, what will this have on the stopping potential? Well, if we increase the frequency here, this value is going to stay the same because that depends on the metal. So the kinetic energy of the electrons is going to increase. If the kinetic energy of the electrons increases, then that means the stopping potential will also increase. So we need to explain this. If the frequency it's not working, of the electrons, nope, my apologies, the frequency of the photons increases, their energy increases. So the maximum kinetic energy of the electrons increases, and so the stopping potential increases. So you're booting them out with a bigger kick, so they go faster, so it's harder to stop them. And that is question 5.